Okay, so we just did this example of finding the bounds of integration for this random shape, which was a little trickier than that first rectangular shape we worked with. And I worked through it kind of the way that you might if somebody gave you a bunch of equations and you just had to figure out how to fill in the bounds of integration. But as these problems get more and more difficult, those bounds are going to be harder to find. And so it's really important that we understand what we're doing when we fill in these functions. That's what we're going to talk about now. So how does finding the bounds of integration work? And before we talk about this 3D problem, I'm going to take us back to thinking about our 2D problems again. So let's do two different pictures. Let's say we had this region R, and let's also think about, oops, it's a little crooked. This region R. And let's just talk about how we set this up because it'll help us build intuition for how we'll set these 3D things up. So real quick, let's just give us some equations to work with. That's a half. Okay. So if we were trying to set up this region right here, we would say, okay, y goes from 0 to root 1 minus x squared. X goes from 0 to 1. And the reason we decide that is we go bottom to top tells us the bounds for y. So we start at the y equals 0 line, and then we go up to the edge of the circle, x squared plus y squared equals 1. Then to fill in the x, we go left to right. But we don't repeat using this curve, so it's not like we wrote x goes from 0 to root 1 minus y squared. The reason we said we couldn't do that is because y is gone at this point. We could never get rid of it if we did that. And so we use this like wording of it has to be the furthest right and the furthest left. And so we said, okay, well, the furthest left was 0, but the furthest right is 1. Even though x is bound in another perspective by that curve everywhere, once we have already dealt with the curve, it's really bound by 1. And so real quick, I want you to think about the shadow of x squared plus y squared equals 1. So if you had, like, the sun is up here. Well, the sun is right above your surface. And it casts the shadow of this line down onto the x-axis, or the projection of the curve down onto the x-axis. It fills up all this space. This part of the x-axis is dark if there's a light above the curve and the curve blocks light down. This part of the x-axis is light. And so that shadow pushing down of the curve from 0 to 1 is exactly the bound we picked for our x-axis. And so let's do this example real quick too. Again, we'll do dy dx. Y starts at x and goes up to 1 minus x. I can see that. Bottom, top. Okay, and then my x-axis, when I find the bounds for x, I go furthest left is 0. Furthest right is this point where the two lines come together, which happens to be a half. If you want to do the algebra to figure that out, you're welcome to. And again, we're going to think about the shadow. Oops. of the line, of both these lines, y equals x and y equals 1 minus x. And again, it's going to just be blocked out everywhere that the lines happened. And it's going to end at a half. So all this area beneath the shape, the region R, is blocked out. And that gives us our bounds for x, 0 to 1/2. And the reason I did this kind of like weird painstaking thing is because this intuition is exactly what we use to fill in the second and third bounds going outward, the ones with respect to y and x for this type of problem. Oops. So what we're going to do is we're going to think about the projection of the surface. Oops. Slash object slash solid, whatever you want to call it. Into the xy plane after integrating z. And then the projection of the line onto x-axis after integrating y. And this is assuming that order of integration where we did z first, then y, then x, just like in our example. And so in our example, the shadow of this surface ends up being exactly this semicircle, quarter circle, because it's just a plane cutting a quarter circle diagonally. And then when we did the x bounds, that actually is exactly like this picture we did, where we had that little quarter circle, and then the x bounds end up being just from 0 to 2 because it was a slightly bigger quarter circle.